Good afternoon, everybody. This is Gene Bohinski with IR Thermal Systems, and the title of this webinar is Improving Process Heating Efficiency and Product Quality Case Studies. And in this presentation, we're going to be concentrating on IR Thermal's experience deploying heating technologies and solving process problems. Let's get started first with a little bit about our company. We were founded in 2020 after the former management team purchased the assets and intellectual property of Radiant Energy Systems and Anderson Thermal Devices. So the management team and employees have had experience since 1985 in this market. Our core competence is the design and manufacture of custom engineered process heating solutions for improving performance and lowering production costs. We focus on quality and dependability. We constantly invest in the latest manufacturing technology. We produce our own high-quality component parts to control our quality. We're focused primarily on continuous heating processes, like one shown on the right in the picture. What's important to know about us is that we're technology independent, so it allows us the freedom to choose the best heating technology for the customer's application. So we focus on custom process heating solutions that cover applications of preheating, drying, and curing. We do hot air systems, infrared systems and heaters, and combination hybrid infrared and hot air systems, where IR is really the booster of the process. We increase line speeds, reduce energy costs, save space. We level out uneven temperature or moisture across a web, and we can heat selected zones across the web effectively with our combination technology. Industries we serve include converting, paper, film, and foil, printing, nonwovens, plastics, adhesive lamination, batteries, medical devices, filter media, fiberglass, advanced composites, industrial fabrics, automotive, packaging, wire and cable, textiles, and many others. We cover three major applications with our drying and heating systems. First is drying for solvent vaporization and evaporation. Curing, which is a final web coating temperature requirement, normally following a drying requirement for modern paints and powder coating. Also heating, raising the temperature of a product to heat set, heat before lamination, 100% solids applications like silicone coating, foils, etc., and metals. And we offer a wide range of drying methods. We have convection hot air systems, which include impingement drying, flotation drying, through air systems, and some batch dryers and ovens. We also do radiant heating and drying systems, electric infrared, and gas-fired infrared, so two energy sources, and combination infrared and hot air systems. We found that each technology has their advantages and disadvantages, and since we're technology independent, we are free to choose which is best for your application. So let's get started with the case studies. The first one is embossing. We were working with a manufacturer of commercial grade wallpaper, and they had an operation that required embossing textured pattern evenly across the 62-inch wide web. Their existing heated steam roller was not providing sufficient heat evenly across the width of the material. So we chose to add medium wave infrared heaters at the following results. Using 3 infrared heating zones across the machine direction allowed boosting the edge temperature for even heating across the entire 62 inches length of material. Using cooling rollers and medium wave infrared heaters allowed only the side needed embossing to receive the heat, while protecting the other side of the web and the soft coated impression roller from being damaged due to the heat. Line speed was increased due to less heating time required prior to lamination. And so the scope of work included us, the IATS team, to review the application and recommend all process changes. We supplied the infrared heaters, the water-cooled roller assembly, the heater controls, and infrared thermometers. In addition, an I-beam mounting system allowed the entire assembly to slide out of the production line for maintenance, and threading was incorporated as well. We also provided on-site installation and commissioning for this application. And here's a drawing of what we did. You could see here the existing steam roller and the web coming in and going around the steam roller and then coming back through the medium wave infrared heaters and through the embossing rolls right there. That's where we added the infrared heaters. And this is a picture of the actual system. So you can see there how we placed the heaters on the right and how the web was going through that assembly with those rollers there. So the next application to discuss, the next case study, is our annealing application with polycarbonate jugs. So we were working with a manufacturer of polycarbonate 5-gallon water jugs. They had a quality problem. When the bottles became filled with water, they became heavy and more prone to rough handling. Bottles were cracking due to plastic stresses caused by the molding process. The solution was to anneal the water bottles after the molding process, but before filling. This involved bringing the bottles up to 180 degrees for 30 seconds. Quartz-faced medium-wave infrared heaters were arranged in an array around the bottles. To heat evenly, the bottles are rotated as they pass through the oven. Annealing the plastic takes away the brittleness and softens the plastic to prevent stress cracks. So ITAS developed an oven design to address these problems, and we've actually deployed quite a few of these ovens across the industry, and it's been very popular with some of our customers. So we developed the oven, we developed these following features. Number one, rotating the bottles as they pass through the oven allows even heating all around. We have thermocouple feedback used to maintain consistent oven temperature. It's very important with the plastics. We have an overhead chain conveyor that allows easy manual loading and unloading without stopping the conveyor. LED indicators give operators visual confirmation that the heaters are operating. Heater positions within the oven are fully adjustable. Lift-off doors for easy cleaning and maintenance were included. And additional heaters were added to allow for another heating zone for bottles with carrying handles. A second design was manufactured for automatic robotic loading and unloading of bottles. Guide rails in the oven rotate the bottles twice to ensure even heating on all sides. So we've constructed many of these bottle annealing systems worldwide. It's become one of our standard designs. They have been proven to be effective and have been low maintenance. So here's some diagrams of how these things work. You can see the jugs and how the bottles are moved through the oven. In the next slide, we have pictures of both the robotic loading system on the left and the manual loading system oven on the right. It's proven to be very effective for that application. So our third case study is for a tier 1 automotive seating supplier. This focuses on lamination. So a tier 1 automotive supplier of car seating required a heating system to melt adhesive powder on a 62-inch wide foam prior to lamination. To ensure a good bond, both the foam with adhesive and the fabric are simultaneously heated. The foam with dry adhesive requires more heat and dwell time than the fabric does. The solution was to build a longer heating section for the foam and adhesive. In addition, this dry adhesive melting process produces a lot of smoke and steam, so exhaust slots were provided between the heaters. Infrared thermometers are used to maintain consistent temperature throughout the heat zones. All heaters are mounted on rails for easy removal and maintenance. This is another one of the dryers that we've developed and have deployed in multiple locations. Some features of this dryer: that we have separate heating zones for foam and fabric material, separate heating zones for the nip roll lamination area, further bias zoning of the left edge, center, and right edge of the web in machine direction to maintain even temperature across the web. We have an infrared thermometer feedback used to maintain consistent product temperature in each control zone. And an exhaust blower is used to remove the smoke and steam caused by adhesive melting. Heaters slide out on rails for quick replacement or maintenance, and lift-off doors are included for easy cleaning and maintenance. We've constructed many of these laminating systems worldwide. They have been proven to be effective and low maintenance as well. So here's a diagram of the heater. You can see the foam web traveling below, and the heaters above it. See how that web is carried. And you also have a fabric web travel that's also heated. So the two are put together with the lamination roll there, or the bonded web travel there at the end, exiting. Here's a picture of the actual heating system. It's, like I said, it's proven to be very popular with our customers. So for the next portion of the presentation, we have Jason Allington, one of our heating experts, that's going to take us through our troubleshooting roadmap using the PID diagrams that we develop and supply with our heaters. So Jason, it's all yours.
All right. Well, we get brought in on existing equipment often for diagnosing, one of two scenarios. The first being it's an existing piece of equipment that over the years, for one reason or another, has stopped working the way it was originally intended for, and the other being that they are looking to increase capacity by either running faster or running new products. And my number one tool for diagnosing what variables I have to work with is the process and instrumentation diagram, or the PNID. And this is something that we develop on all of our new systems during the design and build process. And it's basically a visual representation of every variable and every manual or digital tool that I have to play with within that system. It should show all the automated hardware, control set points and feedback where they are, as well as any manual adjustments that are available within the system. Using this tool allows the operator to step through a system and notice what variables are upstream and downstream of any. It's always extremely important to not only check but also go out and visually inspect. Say I'm changing a damper, I want to visually inspect that in fact that damper is changing. And the importance of this document is that 10 years down the road, when after the machine has been built and operating, this gives me a quick and easy, like I said, it's a roadmap of where changes can be made within that system, or what variables I have to expand the capacity of that system. And it's usually the first thing I print out prior to going out on a new job. Oh, it's not. Oh. So to go through a couple of examples of how I might use this PNID, here's a zoomed in version of the one that I was showing before. And so a common issue that can occur over time is that a box might all of a sudden become positive with positive pressure. And what that means is that you'd be either getting hot air or hot air which containing volatiles that is burping out of the entrance or exit slot of that dryer, which is not something that's often liked. So they would be able to see the reading from the PLC on the pressure transmitter that's located in the box. It's also important to go verify that usually there's a gauge on that transmitter, and you can see that it is in fact at a positive pressure. The first step in diagnosing, you know, is the root cause of that issue would be, in this case, that pressure transmitter feeds back and controls the fresh air that's allowed into the system. Since this is a circle, there's a certain amount of air that needs to be taken out of the system and a certain amount of air that needs to be brought into that system. So if the system is positive, that would mean that the fresh air damper should be closed off completely, because you want to allow less air in. If it is in fact closed off, then I have to look elsewhere for where my issue might be. So I would trace that stream, trace the airstream upstream of it, and I'd say, all right, the next thing on that leg is my exhaust. And I would verify the set point and the physical position of this exhaust damper. If this exhaust damper is all the way open and my exhaust fan is running at capacity, then this isn't yet not the problem. It's trying to get more air and it's not getting it. I would then trace it up further, and now that there are two sets of manual dampers that are controlling the air that's allowed to actually leave the dryer box. Because once again, we're putting in more air into this dryer box than we're pulling out. By the manual positions of those. During a commissioning of a dryer, we would manually once and balance the entire system, and we'd usually scribe, mark, and document where they were sitting at, so it'd be easy to identify if these were in fact changed. If they, then my guess would be that we have some sort of and visually inspect and find where that clog would be. Another example of how this might be useful comes from a recent visit that I had, where a customer was looking to increase the overall capacity of their line, which means they are looking to output more energy into the product. So, looking at their PNID, we went and verified that, in order to increase the amount of energy into a product, there's two ways to do it. You can increase the amount of velocity and volume of air that you're feeding to the product, as well as increase the heat within that air by raising the temperature. In that case, it was a quick diagnosis. Their heater was maxed out they had about a 240-degree delta of the air across the heater, as well as their VFD was maxed out. So the system could not be turned up anymore. Using the PNID, the next variable I had to work with was the fresh air coming into the system. Now, this is, of course, ignoring a major rebuild of redesigning the heat system. So without being too intrusive into their operation, we figured out that they had 60-degree air coming into this system. If we were to install an inline heater and raise that 60-degree air up to 160 degrees, that 240-degree delta across their heat source would no longer go from 60 to 300. They'd go from 160 to upper 300s, maybe 400 degrees. So that seems like the process that we're going to go through there. And once again, it's the PNID was a pretty simple one, but the PNID gave us all the variables that we were allowed to work with. On the next slide is another job I was recently out for. This was a case where they had this extremely large system, and there were actually two things that happened simultaneously that made the customer think that the system was not running correctly. They had shut the system down. We had done a upgrade to the amount of fresh air that was brought into the system in order to run some new products that had a higher volatile content. During that rebuild period, they also went through and did a deep cleaning of that system. So when they were completely done with the rebuild and done with the cleaning, they went to fire the system back up, and they found that they were unable to run at their previous capacity levels. They were not able to meet web speed and still get the product dry. And they'd spent a lot of time, on their computers, on the PLC, evaluating how the system was being set up, and they were unable to figure out why it wasn't operating correctly. So it was a quick and easy stop in for us. I printed out the P&ID. We went out and sat down with the customer. We changed out different, they had already changed out all the pressure transmitters, and we started doing some experiments, raising and lowering velocity. And once again, we were unable to see why the top nozzle velocity was not operating in collusion with the lower velocity. We'd raise the lower velocity, and the top velocity would just stay the same. And after looking at the P&ID, we went through and found a very simple fix, in that during the cleaning process, somebody had gone through, and right here are some manual dampers that they had closed off in order to clean both sides of the blades. And it was really that simple. The marks were not lining up. They opened up the dampers, and the system went right back to how it was originally when it was commissioned. So that's just kind of a story about where it's not only do you have to verify digitally that the changes you are making are happening, but you also have to go out and physically verify that the changes you're making are actually happening. So, and those are just a couple quick examples of how we evaluate systems that aren't working correctly, how we might evaluate a system on where we have the ability to expand, or we're evaluating new systems based on existing systems in order to give them the most amount of flexibility they have and still maintain what is important to their process.
Thanks, Jason. That was great. All right, just a couple more slides. Looking at some of the other applications that we focus on. Once again, we make infrared heaters in both gas and electric versions. The electric has a wide temperature range, a better turn down for infinite temperature control and tunability, with a maximum of 10 to 55 watts per square inch. With gas, you have a higher density of heat that allows higher temperatures and high intensity heat in a small package, the 50,000 BTU per square foot, which is 60 to 100 watts per square inch. So it's quite a lot more than the electric heater. So it's more intensive medium wave heating. The choice of gas or electric might be made by local energy costs. Those things are changing all the time, but it also varies by location in the world. And they're often used to cure powder coatings on any substrate. The other thing we focus on with a lot of our customers, and a lot of the things that we've heard today, were combination or hybrid dryers, where we combine hot air with infrared. So we specialize in developing hybrid dryer processes, combining the best of both worlds. We do combination convection infrared that can be designed together for your application, or a combination of electric and gas infrared. The IR section is often used as a booster to existing processes, as you've seen with some of the things we've worked on. It allows a faster warm-up of the web in the process. It helps increase the line speed of existing processes. It expands the production capacity of existing equipment in the same footprint in the facility. And we can improve overall process temperature consistency. And on top of that, we offer a rental heater program. This is a great way to learn how to use infrared, because we found that it's very useful, that there is a learning curve when it comes to deploying IR heating in your existing process. And we often rent these heaters out. We have them available in widths from 12 to 84 inches in 240 volt, 480 volt single or three phase. Rental packages include the heater, the blower, and the control panel. It's designed for a quick trial setup. They're plug and play, and rental terms are as short as 1 week are available. Test units are available for running trials in your facility on your line. That's the main purpose, so you can test them out in your existing line. So at this point, we reached the conclusion of our presentation, and now it's really time for your questions. We have our application experts on the line. You can email us in the future at info@irthermal.com or call 833-Oven Dry.